So this is from very recently, 30th of June, 2025. And the idea here is that this software engineering benchmark provides a benchmark for LLMs to target to determine the usefulness of LLM output in terms of code. Let's read this, shall we? Large language models and their agentic frameworks are increasingly adopted to automate software development tasks such as issue resolution and program repair. While prior work has identified security risks in LLM-generated code, most evaluations have focused on synthetic or isolated settings, leaving open questions about the security of these systems in real-world development contexts. In this study, we present the first large-scale security analysis of LLM-generated patches, using 20,000 plus issues from the software engineering bench dataset. We evaluate patches produced by a standalone LLM, Llama, and compare them to developer-written patches. We also assess the security of patches generated by 3 top-performing agentic frameworks, OpenHands, AutoCode Rover, and Honeycomb, on a subset of our data. Finally, we analyze a wide range of code, issue, and project-level factors to understand the conditions under which LLMs and agents are most likely to generate insecure code. Our findings reveal that the standalone LLM introduces nearly 9 times more new vulnerabilities than developers, with many of these exhibiting unique patterns not found in developers' code. Agentic workflows also generate a significant number of vulnerabilities, particularly when granting LLMs more autonomy, potentially increasing the likelihood of misinterpreting project context or task requirements. We find that vulnerabilities are more likely to occur in LLM patches associated with a higher number of files, more lines of generated code, and GitHub issues that lack specific code snippets or information about the expected code behavior and steps to reproduce. These results suggest that contextual factors play a critical role in the security of the generated code and point toward the need for proactive risk assessment methods that account for both code and issue-level information to complement existing vulnerability detection methods. They continue with some of the details. I won't read all of it, but we'll get to some of the details there. It's very eye-opening. They reference some studies that show 30 to 50% of code generated with AI code assistance contains vulnerabilities. And so they discuss the outline, which is, well, we want to make sure that we understand what's going on and some of the risks, etc. So here's our rubric. We're going to ask a few questions and we're going to get into it, yada, 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 yada. So they evaluated the LLMs on 20,000 plus GitHub issues. The standalone LLM introduced 185 new vulnerabilities, nearly 9 times higher than the 20 new vulnerabilities introduced by developers. On a smaller test of 2,200 plus issues, the agentic frameworks also produced vulnerabilities, with the highest counts observed in the framework that gave the LLM greatest autonomy. The more autonomy you give the LLM, the more likely they are to introduce issues. The Llama LLM produced 9 times more vulnerabilities, including some high-risk vulnerabilities that were not in place by developers to start with. In other words, these LLMs produced new vulnerabilities, new patterns, new behavioral patterns, and introduced it into the code. These findings suggest that the risk of generating vulnerabilities is not only a function of the code produced, but also of the context in which the LLM operates. They continue with their process. This is kind of their process. They lay it out in this chart. They down here, towards the end here, they ask the research questions and come up with the answers with regards to those questions. They go over the empirical data, yada, 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 the characteristics, how they determine that something is or is not something. It is worth noting that all reported numbers are the new vulnerabilities that were injected only after the LLM developers modified the files or added the code to the repository. Okay, this is important. You have to remember that it excludes the idea that the LLM generated a bajillion other outputs that were bad. They strictly focused on what ended up inside the code at the end of the day. This was really important so that you You don't have like a bias on, oh, it created a bunch of stuff. Like developers do this too, right? So they did a proper exclusion here. And then they looked at the kinds of vulnerability for the programmers out there. Here's an example of a piece of code that the LLM produced in Python. Check password function, which includes a vulnerable use of hashlib.md5. There are a few others. Okay, they go over a few others, like failing to do SQL injection checks, like this, right? There's no SQL injection checks here. There's all kinds of stuff they cover, right? So they actually looked at the code to figure out what went wrong and what the LLMs produced. Across all systems, vulnerable patches typically modify more files and file types and involve more generated code. Higher risk patches in ACR exhibit abnormally high code complexity. Let me go to the patches level. If I go down to here, let me look at the patches. Okay, now one question that I did have, so right here, we'll zoom in on this. They did 22,000 plus GitHub issues on LLM. Or sorry, on Llama. And I thought to myself, why couldn't they do that many on the agentic ones? And here's the reason. While our LLM-based approach generated responses for both the train and test sets, a process that took well over a week, we acknowledge the limitation of our agentic study in terms of data scale and have adjusted our conclusions accordingly. They had to scale down. Why did they have to scale down? For example, AutoCode Rover reports a cost of 70 cents per instance to achieve their test set results, meaning it would cost over $13,000 to generate patches for the full 19,000 instances of training set, which is beyond our available resources. This completely undoes the argument of people who say AI will just fix AI issues. Oh, really? Will it? Because you have 2,200 issues here that would have cost upwards of $13,000 to fix with just one agentic LLM. What does that mean if you have 22,000 plus issues on a subset of GitHub repositories, a small subset of them? We have decades worth of code out there that needs to be fixed. And then you're going to generate even more insecure code at a rate of 30 to 50%. In some cases, 9 times more vulnerabilities created than developers themselves create. And then who's going to pay for all that? What's the price cost of that? Let alone the energy cost and the time that it took to do it. You think AI is going to fix all this? This completely undoes those arguments. And we haven't even talked about context, because I don't think a lot of people know what context is.